our first speaker is a collaborator of Michael's from that period of time, and a long-term collaborator, Bob Pego, who will tell us some merging and splitting stories and their dynamics. So, Bob.
Well, thank you very much, Panos, and thanks very much to all the organizers. I'm really pleased to be able to participate in this conference in honor of Michael. Okay, I've been blessed with a lot of fine collaborators, and Michael was one of the earliest. It was always enjoyable working with him, and very productive. I just want to express my gratitude for his friendship over these many years. So thanks very much. The topic I chose for this talk actually goes back to those early years, or at least started then. Joe Keller was visiting Ann Arbor, where we both were, and he said to us, as he used to say to young people, I guess, or said to people who used to be young, I don't know, tell me a story. So I started this story about characterizing self-similar scalings in size distributions. And well, it took about 20 years to complete the story, but I'm happy to kind of mimic Paul Harvey and say, this is the rest of the story. And then, well, with the tools that we developed for that, it took a long time to kind of come across. I've been working with Jean-Guo Liu and Pierre Degon recently about a problem that came up in discussing animal group size. Now, this one went a lot faster, but it's a lot of fun too. Okay, so coagulation equations, you're going to see them in a little while. They're kind of like Boltzmann equations. They're integral differential equations, resemble kinetic equations, and a lot of the mathematical analysis are related to techniques in kinetic theory in general. But these are really simple equations. I think of them as sort of poor man's Boltzmann equations. But because of their simplicity, they appear in a lot of areas of science. So astrophysics, aerosol physics, that was a big area for a long time, kind of the formation of aerosols like smogs. In material science, so anywhere you're interested in a size distribution and things coming together, these kind of equations are likely to appear. Well, in the recent decade and a half, roughly, in probability theory, a lot has been done related to these things, having to do with, well, random graphs and ancestral lines of descent. But in particular, a nice connection appeared to random shock clustering models. Those things I won't talk about, but I'm going to go back kind of to the beginning, how I got interested in these things. So I was working on Allen-Kahn equations, so I won't write those down, but reaction diffusion equations with domain walls that interact very weakly. So John New had figured out formally how these things work. I was working on that. And a kind of cartoon for how coarsening happens in this Allen-Kahn pattern coarsening is that the domain walls, there's a lot of them on the line. And, well, the nearest two are attracting each other the strongest. And so, okay, a cartoon is simply that those things come together, they annihilate, and you're left with a pattern with fewer domain walls, right? Two fewer. So you just repeat this over and over again. You start with thousands or millions of these walls, and it's very simple to simulate. So what simulations show is that the domain size distribution, that's the key statistic here, approaches a self-similar form with various initial domain size distributions. So n of s and t, n of t and s, I think of as a density for domains of size s. Okay, so roughly speaking, sizes between s and s plus ds, this counts the number of those domains per unit length on some large scale. Okay, so here's the simulations, really old results of simulations. So this is an example. I'm just starting with a uniform distribution, domains between sizes 1 and 3, so density a half. And you start this off, and the smallest domains have size roughly 1, and they combine with 2 other domains. And so the new domain is like at least 3, so it's bigger than 3 typically. So after a bunch of the domains are gone, so the next one, a bunch of those smallest domains are gone, original domains are gone, there's a kind of peak, sizes between 3 and 5, and you've got, well, higher peaks, and this goes on for a while. Well, so 25% are left. There's very few of the original domains left. And 5% are left. you're pretty close to this solid curve here. And the solid curve was produced by the theory we had at the time, so which I'll describe in a second. It's a self-similar solution with this Laplace transform. The Laplace transform of n star, the profile, is the tangent of half the exponential integral. So you'll see how that occurs, but that was about as far as the story went that I could tell Joe and Michael. Well, except for this. So how did we get that form? We wrote down the rate equation. So this is the kind of weak poor man's Boltzmann equation. We're saying the rate of change of intervals, of the number of intervals of size s, is driven by, okay, the frequency that these collapse events are happening. And in this case, capital S is the smallest size. That's a prescribed function in this model of T. You prescribe how fast those things are disappearing. So that's the number of smallest domains that are disappearing in a given in an interval of time. And then for each disappearance, well, each domain of size S has a neighbor S hat, either on the right or the left, so that it accounts for a factor of 2. And this is like the probability that the sizes have those sizes. So that's a loss term for domains of size S. And to gain an interval of size S, well, it has to combine with S hat and little s minus capital S minus S hat. So that term looks like a convolution, except there's got this nasty delay in it, capital S of T. Okay, so about all we could do at that time was to say, well, we'll look for a self-similar solution, and you'll see in a minute how we can do that. And we could find one. We could show that it really was physical. So there, the story sat for like a dozen years with nothing happening. Okay, that's this nature. This capital S of T just obstructed all progress. Okay, but then Thierry Gallet and Alex Milke came along and had a bright idea. So I'll describe what they did in a second, but at the end of the day, the solution procedure they come up with can be described this way. It's rather strange. So you take your size distribution, which is, well, I should say that n is, the density is 0 when S hat is below capital S, right? And there's no domains of size less than capital S. Okay, you take the Fourier transform. Then you compose with the inverse hyperbolic tangent, so log of 1 plus z over 1 minus z or something like that. And you take the inverse Fourier transform, so kind of a nonlinear pseudospectral analysis somehow. And then the solution is given by this formula. So you take the initial data, and you just cut it off. So they use a particular minimum size function. It doesn't really matter. So when small s is bigger than the capital S of T, it's just the original initial data. And when it's less than capital S of T, and as capital S of T is growing, you just set it to 0. You just kind of truncate it. So that's kind of strange. But they also got a number of very nice results, not necessarily using that formula to analyze the problem. But they proved a well-posedness theorem for L1 in initial densities. They found a whole zoo of self-similar solutions, including ones with, well, fat tails. Let's see, what do I have here? Well, that's the power law of decay. So theta equals 1, I believe, in that case, you get an exponential tail. But there's a zoo of solutions with power law decay. They obtain sufficient conditions for approach to self-similar form. And actually, the rate of approach to self-similar form depends on how close the tails are to the initial data, and to the self-similar solution. So they got a variety of these rates of approach. So this was coming out about the same time that Govind Menon and I were analyzing the simpler Smoluchowski equation, which includes, I guess it's an equation like this without this delay capital S, just a very classical one. And so we had a number of results, which I won't be describing today, but somehow choosing the time scale so that the total number of domains that are in the system, which is decreasing with time, is continuous, is kind of key to getting a well-posedness theorem for arbitrary finite measures. So then one reason we chose this one was it mapped nicely to our theory of necessary and sufficient conditions for approach to self-similar form. And after a few more tries, well, we managed to handle this model too, the one with this funny delay capital S of t. There's also a result on characterizing eternal solutions. So this has to do somehow with the notion of scaling attractor, which if I start to talk about that and its relation to infinite divisibility, I promise I would be here all afternoon. And it's really interesting, but I'm just going to leave it aside today. OK, so let's see. Oh, yeah, I want to describe the solution formula and what the characterization theorem is. OK, so here's I've taken the capital N out and written down the rate equation. A kind of natural weak form for solutions that don't necessarily have densities is to multiply by a test function a of s and integrate. So then let's see, capital F is a normalized cumulative number density. So that's a probability distribution, a CDF. And so F sub t ds, that's a probability measure. And the rate of change of some generalized moment of the thing is given like this. So this term is coming from the generation of a domain of size capital S plus S1 plus S2 from neighbors of size S1 and S2 and the minimum size. And then, OK, this thing is normalized, so you don't see all the loss terms that I would normally write down. So but there's this capital A of S. OK, so it's natural in a problem that involves convolution, which is kind of what I've been hinting at here, to look at the Laplace transform. The Laplace transform converts convolution into multiplication, right? OK, so but e to the minus capital S comes out, e to the minus q capital S. OK, but otherwise the convolution turns into this quadratic, and capital N is 1 over t, so that's here. So you have this equation here, but there's this capital S that's unknown. And it's kind of stymied us for a while. And of course, you separate variables and try to integrate. So when you integrate, you get an inverse hyperbolic tangent from the primitive of this left-hand side. And so you can write capital F bar, that's the Laplace transform, in terms of, well, the integral of the right-hand side. So somehow we didn't realize, Gallia-Milka did later, that you should integrate to infinity. And then it's rather difficult to realize that you're staring at a solution formula. Because what happens? So at time t naught, the data determine, OK, F bar t naught. OK, but it turns out that determines this capital S. Capital S I call the min history, the history of the minimum of the domain size. Somehow you can imagine that by changing variables to capital S as the independent variable, you get a Laplace transform of something there. And so basically this capital S is determined by this initial data. And so once capital S is determined, OK, all you do is truncate at time t to determine the solution at time t. OK, so we like to use that to actually analyze the dynamics of this in a kind of general way. And one thing that happens is that, well, capital S has to be a power law for this to be self-similar. And then a change of variables turns the profile into a hyperbolic tangent of, well, a constant times an exponential integral. So that accounts for all the self-similar solutions that Gallia-Milka had. And they had this formula. So. OK, so what's the theorem here? This is necessary and sufficient conditions for, well, approach to self-similar form in the weak topology. And the topology that corresponds to pointwise convergence of Laplace transforms. So Laplace transforms are convenient for this. Let's see, so we take an arbitrary initial probability measure with positive min, so s at time 0 is positive. And okay, the f sub t is the solution. Suppose that there's some way to scale the CDF as time goes to infinity, so that converges to a probability distribution with positive min. So I'm not putting any restrictions on what that scaling is, just scaling in some way. Okay, well then, actually there's a condition that the limit has to be one of the self-similar solutions we know. And moreover, the initial data has to be almost like a power law, have to have almost power law tails. So the precise way to do that is there's a slowly varying factor, and I'll say what that means in just a second, times a power law, which describes the asymptotics of the first moment. Let's see, the way that the scaling has to go then is more or less asymptotic to a power law. That's coming from the slowly varying factor like this. Okay, and that's necessary, and it's also sufficient. So one really characterizes this. So where this kind of theorem came from was kind of our earlier work on simpler versions of the Smoluchowski equation, and we realized that actually the technique that's most useful for analyzing this comes out of probability theory. So we're just reading Feller's beautiful book, okay, written, I guess, in this town, on the central limit theorem and Levy's stable laws and infinite divisibility. And each chapter that we could read on that, we could write a paper about Smoluchowski equations. It was just a pretty nice experience. The techniques has to do with, they don't have to do much with probability, they have to do with analysis, and really some classical kinds of analysis having to do with scaling limits. And so the key tool is a very simple lemma that you find in Feller's book, having to do with scaling limits of a single function. So take f. In this case, well, suppose it's monotone, although the most general version here is just measurable. Okay, and you scale inside with lambda j's going to infinity. And you scale outside, there's some weak condition that the normalizations can't vary too much as j goes to infinity. So you suppose that this shape, after you scale, that there's a limiting shape. Right, and somehow the result here kind of explains why physicists are interested in power laws. There's kind of a scale invariant measurement has to come from a power law, has to correspond to a power law. Okay, from my point of view, what's interesting is that there's a necessary condition on the f that you started with. Namely, it has to be almost power law to begin with. So the technical condition is regular variation. A power law times a slowly varying factor. Slowly varying just means that rescaled versions of itself are flat. Rescaled versions converge to 1 for every c. Okay, what's pretty amazing about that condition, this pointwise limit of rescalings actually implies uniform convergence. So you're getting a lot more out of this than you put in, kind of like complex analysis, almost like that. So it's a beautiful theory. There's books written on this condition that we eventually plugged into. So that's the key tool. And I want to just kind of rather quickly sort of sketch how this tool comes in to this problem in a rather delicate way, which took us actually a long time to figure out. So, okay, so we're asking that the scaled versions of f sub t converge. So in the Laplace transform, the scaling goes the other way, q over lambda, and those have to converge. Okay, we write what that means from the solution formula. The hyperbolic tangent goes out, and this thing inside, q over lambda is here, and that has to converge to something that corresponds to the limiting solution. Well, okay, so then it comes out of that this ratio here, this scaled min history has to converge. All right, well, the min history is one function. Its scaling limit has to exist. Basically, by applying the scaling rigidity lemma, you deduce that the limit has to be power law, And the function you started with s had to be regularly varying to begin with, almost a power law. OK, so now if you know that the min history is regularly varying, you want to go back and infer something about the initial condition. And this is done through Tauberian arguments, which in this case are rather strange and delicate. So it turns out that, let's see, how is this? So that the Laplace transform of the initial data is a hyperbolic tangent of an integral. That integral is here. It turns out to be the Laplace transform of something, a function whose exponential is the right inverse of the min history. So it's a kind of unusual, I referred to that change of variables. So it's a change of variables, and then the Laplace transform of A appears in the solution formula. OK, but that hyperbolic tangent comes in with an exponential. OK, well, trolling the literature, for years or whatever, there's this handy exponential Tauberian theorem. So ordinarily, things like regular variation, they transform very well under Laplace transform. But here we have a regular variation of s, which is the exponential of a. Luckily, this smart analyst Dehaan had figured out something that applied to that situation. The exponential of a bar, knowing that it's regularly varying, the exponential of a itself, with an inversion of the argument, is regularly varying, with this nice little factor that involves the Euler-Mascheroni constant. So it's a beautiful little theorem, and it's just perfect for this situation. E to the minus a bar is therefore, because it's regularly varying, I can infer the same thing about a. No, it's the other way around. So s was regularly varying. The inverse of s is regularly varying. That's regularly varying. So therefore, a bar is regularly varying. Therefore, e to the minus a bar, that means, well, 1 minus f. 1 minus f bar is regularly varying. That behaves like a power. OK, once I'm down to the Laplace transform, I can more or less use standard Tauberian arguments. What you've got to do there is differentiate with respect to q roughly, and then an s comes out. And then the standard, you have q to the theta minus 1, that transforms into s to the 1 minus theta by standard Tauberian theorem. So what I've put in color here, though, is one of those small hints that nature sometimes gives you, that this is a better function than the original Laplace transform. This thing that involves, it's really the integral of a Laplace transform. Its derivative is a Laplace transform. OK, so that's how the characterization theorem goes, and how we know what basically all the initial data that correspond to self-similar limits are. OK, so I don't tell the story about what happens when you don't have such data, but OK, we'll go continue. OK, but the story really continues from here. These functions whose derivatives are Laplace transforms. And it gives us into the second half. So this is the merging splitting dynamics for animal group size. So that function whose derivative is the Laplace transform is now called a Bernstein function. So there's this lovely book from 2010 by Schilling, Song, and von Dratzek about these kind of functions. And the kind of complex function theory that goes into the analysis of these things is quite beautiful, and we managed to use some more fancy versions of it. So this is what I want to show. OK, so we're going to look at pelagic fish. So these are fish in the middle of the ocean. Oh, before I get there, OK, that's Bernstein functions, right? So these are smooth functions whose derivatives are Laplace transforms. Those are completely monotone functions. They're positive. The derivatives alternate in sign. When you have a Laplace transform, you take derivatives. They alternate in sign. And a classical theorem of Bernstein is that that sign-changing property characterizes Laplace transforms. OK, but functions whose derivatives are Laplace transforms, OK, you integrate them and you get functions that look like this. So there's a measure that's involved. And because 1 minus e to the minus qz behaves like q times z, this is the integrability condition on that measure. the minimum of z and 1, has to be integrable against mu. And then there's these two other positive constants, or non-negative constants, that are possible here. So there's a characterization theorem that says phi is Bernstein if and only if it has a representation like this. And what we associate with this Levy triple, so-called Levy triple, is a measure that lives on the extended half-line and includes infinity. So there's a delta mass at 0 that corresponds to this A0. There's a delta mass at infinity that corresponds to the constant A infinity. And then Z min 1 times mu. OK, and the continuity theorem, the thing that makes it possible to do analysis with this, you won't find it in the book, but we had basically shown it in earlier work, is that if you have a sequence of these things, so a sequence of triples corresponding to Bernstein functions phi n and these measures kappa n, then pointwise convergence of the Bernstein functions, this was known that the class of Bernstein functions is closed under pointwise convergence. It corresponds to weak star convergence of the kappa measures on the extended half-line. So you have to take test functions that are continuous at infinity, and that's the characterization that works here. OK, so we'll use this a little later. OK, but the problem that de Gondt pointed us to had to do with animal group size. And this work of this Japanese fisheries scientist. So I understand he spent some time here in Princeton, actually, visiting Simon Levin. And Simon Levin had done some work in the mid-90s on coagulation fragmentation models of animal groups. And so I guess in Japan, fish are important, right? And so the smartest people work on fish. And eventually, Niwa came up with this rather striking hypothesis that the group size distribution of fish in the mid-ocean is described with a single function phi, a single profile, scaled by basically the average group size weighted according to individuals. So n is the number of groups of size s, so s times n of s is the number of individuals in those groups. And so you weight that by s, and you get an expected group size. So you do this scaling, and you plot the data. And there's no fitting parameters. OK, it's quite remarkable how pretty good with. OK, you're talking about rather destructively accumulated data. The trawlers are out there catching the fish, and you have this stuff here. So one of Niwa's points is that the distribution he gets here is very non-Gaussian. And so it's got an exponential cutoff in the tail, but not exponential squared. And a big point is that if you're looking at these large schools that people encounter and using Gaussian statistics, you're going to way overestimate the population of fish in the ocean. So the fact it's non-Gaussian is important. OK, but he actually proposed a very specific function for this profile. And came up with this with some rather sophisticated mathematics involving Ito calculus. This is kind of wild, but to kind of estimate variances, he introduced this coagulation fragmentation process. So what we want to do is take that coagulation fragmentation model, which was then later written down a little more explicitly by others, and try to do some consistent mathematics with it. And we're going to get this function here. So, OK, so the red dotted line, which is there somewhere, is Niwa's function, which fit the data pretty well, as you saw. The new function is a solid line. It's the formulas down here. It has a different power law, not s to the minus 1, but s to the minus 2/3 for small s. And let's see, actually, just a pure log distribution, if you neglect the correction in the exponent here, is there in the green line. Actually fits ours a little bit better. So this is a ratio of Niwa and ours to Niwa and their log to ours. So it's let's say Niwa's is within about 20% of ours over all the decades of, oh yeah, it's something I forgot to say, is that that's 4 decades of data, right? So a lot of variation, and NIWA is doing very well. So I guess what we're saying is we have a kind of more consistent explanation for what's going on here. A story that has to do with coagulation fragmentation. Okay, so what is NIWA saying? So he says, well, you model the ocean as a discrete set of sites. And the fish schools, they jump randomly to different sites. They zoom around the ocean at discrete time steps. If they encounter each other, he assumes they merge with, well, maybe with some probability. But they can also split. So schools can split in 2 with a small probability per time step, independent of school size, and you don't know how they're going to split. You assume that they split with uniform likelihood into all the different possibilities. So it's a pretty simple model. It turned out, though, that the kind of mathematics that involves this is not well developed. It leads to a coagulation fragmentation equation. So these are the rates. Let's see. So Cj is the number of schools of size j, number of groups of size j. There's an accumulation term where j meets k, and that's a destruction term. Size k meets size j minus k to produce j. Okay, and these are the rates that have to do with coagulation. And then the split up rates are here. So Cj is lost by adding up all the destruction rates. And you can gain a Cj by a j plus k decaying into a j and a k. Okay, so the coagulation rates are constant here. Fragmentation rates just depend on the size, so that the overall rate is constant. The overall rate of fragmentation is constant. Yeah, this is a mean field approximation, right? But what's going on here from an analytic point of view is that this model does not have detailed balance. And that means that essentially all methods that we know about from kinetic theory of analyzing a long time behavior are out. Just sort of, you couldn't say anything about this. Okay, so what are we going to do? So actually, the first thing we did was to consider as kind of a simplification by looking at the large population limit, the size continuous corresponding equation. So written in weak form, okay, so nu sub t is the size distribution could possibly be a measure here. In weak form, f is now the test function. You gain something of size s plus s hat when s meets s hat. You lose s and you lose s hat. That's the coagulation mechanism. The destruction mechanism, let's see, is written here as a kind of linear mechanism in the size distribution. Okay, so what we knew from coagulation dynamics when you didn't have the fragmentation term is that this Bernstein function, the Bernstein transform, was the very convenient variable to look at. So that's really the first thing we did, is to try to take the Bernstein transform. And when this equation popped out, kind of just a non-local version of a logistic equation, I couldn't look at anything else for a week. I had to study this equation. You can't resist. Okay, so yes, what happens with this equation? Well, the first thing one notices is there's a dilation symmetry to it. If you just change the scale, it leaves the equation invariant. So there's an equilibrium solution, and it can be scaled with the same profile. So that is one thing that accounts for the universality of NIWA's data. Let's see, you start computing moments. Let's see, the first moment is naturally conserved. It's the total population. That's when f is the identity. This thing is 0. And then the 0th moment, the total number, is actually satisfying a logistic equation. It goes to a constant. It goes to 1 with this normalization. Okay, so what we could analyze. So one thing one looks at is the equilibria. And there's a pretty nice description of what the equilibria look like. So for a fixed finite mass, and if you scale that to 1, the equilibrium measure has an exponential cutoff, I'll explain where 4/27 comes from roughly. The coefficient, the prefactor, is really nice. It's a completely monotone function. And its behavior at near 0 and infinity is power law, crossing over from s to the minus 2/3 to s to the minus 3/2. So s to the minus 1 is a pretty good compromise. That's what Neo was working with. And okay, those things come out of Tauberian theory. I won't say too much, but I'd like to say where this kind of rather nice characterization of the density comes from. Okay, so you write down the equilibrium Bernstein transform, so the equation. So that's this integral equation. And of course, you can differentiate to eliminate the integral. So you do that. So you take the derivative and let's see, you eliminate the integral. You get this nice ODE, separate variables. And you can integrate that. So there's this implicit equation for the Bernstein transform, this cubic equation, essentially. Well, the cube root solution formula doesn't help us much, it turns out. It's just kind of a mess. But OK, so this function, u over 1 minus u cubed, looks like this. It has got a minimum here at minus 1/2. The minimum value is minus 4/27. That's where that exponential prefactor turns out to come from. So one thing you can do with this implicit equation is you can get a power series for the solution by taking the cube root, rewriting things in terms of 1 minus phi, and then you've got something where you can apply the classical Lagrange inversion method and get a power series in powers of s, which gave that power series in fractional powers of s that I had before. So this is a little bit like, let's see, there's these alternating powers of s to the 1/3. Over n factorial, it's a little bit like an e to the minus x, so there's an exponential cutoff. There's these funny factors that are actually singular at every third integer and produce, so every third power of s is not in this, doesn't appear in this sum. But if you use 50 terms from there, you just get a beautiful curve like I plotted. Okay, but this doesn't explain this characterization. So this goes back to that book, the Schilling book from 2010 on Bernstein functions. And I'd seen this theorem there, characterization of what he called completely Bernstein functions, complete Bernstein functions. And I thought, well, I'll never use this theorem. It's rather strange. So you're asking for Bernstein functions whose Levy triple involves a completely monotone density. Okay, so the Levy measure is got a completely monotone density. It itself is a Laplace transform. Okay, why do you care? I don't know. There's this theorem that says that condition is equivalent to a global analyticity condition on the Bernstein function to begin with. V should be Bernstein and actually holomorphic on the cut half plane, on the cut complex plane, cut along the negative axis, with the property that it's a so-called Pig function. It preserves the upper half plane. It leaves the upper half plane invariant. So like fractional roots, like square roots, cube roots are functions like that, and they have this kind of representation. So, okay, well, we've got this implicit formula here, and by George, phi is a Pig function with exactly the right property. Actually, you can transform away that exponential, and you still have that e to the minus 4/27x, and you still have that property. So that's where that really came from. So we got just to apply that theorem from Bernstein function theory. Let's see. So the original model that let's see, the Swedish group wrote down for coagulation fragmentation model from NEWA simulations wasn't analyzable in the terms that we want. So let's see. What we noticed though was that a kind of discretization of the continuous model is still analyzable. Of course, the Laplace methods are fairly fragile, and you can't perturb the equation too much otherwise. So You just change things a little bit and you say, well, if you're splitting a group of size j, you allow 0j and j0 as one of the possibilities when you're counting equal likelihood. Of course, nothing really happens, so the rates get modified a little bit. But it turns out that the discrete Bernstein transform then for the discrete size model is an equation of the same type, essentially. So you have an averaging operator where you average from 0 to q with a weight e to the minus q. Okay, so a very simple change of variables transforms that equation to the same as the other one. And we can really go to town and figure out the dynamics. I'll say something about the dynamics in a minute. The equilibrium situation is not quite straightforward. The complete Bernstein theory really required a continuous a size distribution measure that had a continuous density. And here, we're definitely dealing with a discrete size distribution. So we looked for some analog of the complete Bernstein function representation theorem. And it turned out not to be in there in the literature. It turns out to be quite closely related to some very classical problems of moments, Hausdorff moment problem. Given a sequence Cn, when is it the moment distribution for a measure, say in the interval 0 to 1? So this was characterized by Hausdorff as such a sequence exists if and only if the sequence itself is completely monotone, meaning the differences alternate in sign. So the backward differences all have the same sign. So that's a kind of discrete analog of Bernstein's theorem. But the new theorem actually is that using the generating function of the sequence and the global analyticity properties of that, you can characterize when this happens. So given a bounded sequence, a generating function like this, you can also look at the upshifted generating function multiplied by an extra power of z. Okay, then complete monotonicity, so c being the moment sequence of a measure, is equivalent to this generating function being a Pick function, non-negative and analytic on the half line below 1. Okay, there's some radius of convergence, but it has a global continuation to be this Pick function. Okay, so this is just about almost the last slide. So let's see. So this is so we can characterize then equilibrium of this discrete problem this way, that the equilibrium sequence is actually an exponential cutoff, so a z to the power j, multiplying by a completely monotone sequence with this algebraic behavior at infinity. So that uses that characterization theorem. For dynamics, we can actually analyze that non-local logistic equation and show that there's convergence to this globally to the self-similar solution as long as you have a finite first moment. With an infinite first moment, we don't know exactly what happens, but there's this approach to zero weakly. So everything goes into larger and larger group sizes. Okay, so that's really the recap is there's this new universal scaling off a group size given by the power series. And it comes out of this theory of coagulation fragmentation and in some way explains in some way the scale data. So with that, I conclude and wish Michael a happy birthday.
Right, any questions for Bob? Bob, go ahead.
There's another one.
So at the very beginning, you passed from a picture about particles going through a certain process to sort of a mean field model of it. And my question is, do we understand well how the initial distribution has to be set for the particles in order for the mean field model to be appropriate? I mean, there's certainly some independence built in.
Right, and there certainly are problems where correlations develop.
Yeah, so that's my question is, do we understand, I mean, at least, I suppose, there exists maybe uniform distribution of particles all independent, or Poisson or something. Do we know that the simplest models like that are correctly described by the mean field model?
Let's see. For a model that really has a kind of spatial structure mixed in, the only thing that I think there's few results. So I think of one by Reza Kanlu that deals with justifying the classical Smoluchowski equation through Brownian motion of particles. But in one dimension, Brownian motion of particles and annihilation, kind of like I'm having here, it does not work. Simulations seem to show correlations develop. So here I have something a little simpler that let's see, it's a little bit more like a thinning process in probability, where it's in that case, it's known that the correlations do not develop. But there's precious few results on that kind.
Yeah, so I guess you mentioned at the beginning applications to astrophysics, in fact, galactic clustering. I mean, this reminds me a little bit of some of the profiles you see for like dark matter halos. There's something called the NFW profile. Have you looked, and it looks somewhat like this NEWA profile. Have you looked into that at all?
I've never looked explicitly. I even saw, in Carnegie Mellon, one of the PhDs was on this topic somehow.
Yes.
They were interested in inverse problems, somehow using the size distribution to kind of infer the coalescence rates, for example.
Yes. Right.
There's a lot of interesting problems there, but I haven't looked.
Oh, I see. Yeah, no, could be connected. Thanks.
Any more questions for Bob?
One whimsical question, sorry. How many fish are in the ocean?
Let's see. I was trying to figure out exactly what the data meant here, for example, and I somehow don't have a complete answer. One way that they measure the sizes of the schools is just how thick the schools are through sonar. So how many of these there are? I guess some of the schools still have millions, and maybe could be quite large schools, miles wide. Not many of those are left, as we grew up with the Grand Banks, being teeming with cod, and now they're gone. Yeah, maybe the answer is not many.
Maybe you've answered it already. Are there other data sets to which this has been applied? And well, another question was, do you know something about the rate of approach to equilibrium in the last results?
Rate of approach. Since we use these kind of quite weak topologies, we don't have a good analysis of that. Kind of in the more...
One of your results was on strong convergence.
Yeah, that's right. Let's see. No, I guess I don't have any idea about that at the moment. But the other question was about other data sets. So NEWA has some things on things like animal herds, where things don't fit so well. He liked these pelagic fish because more or less all sites are the same in the mid-ocean, and that's particularly clean, I guess.
Right, if there are no more questions, let's thank Bob again.